Okay, folks, let's get into this next learning goal on the temperature dependence on chemical kinetics. So we're going to discuss the famous Arrhenius equation. And you talked about this in Gen Chem before, but we're going to add a lot more detail compared to what you may have talked about previously. So I'm going to just present to you the Arrhenius equation already derived now. And in the next couple of weeks, we're actually going to derive this equation from the ground up. So what I want to note here in the Arrhenius equation, K here is our rate constant. And we should note that that could be a rate constant of any order. So it could be a first order rate constant, second order rate constant, and so forth. So this A term, this is what we call our frequency factor. And I'll talk about more of this in a moment once I've described everything else. So EA, that is our activation energy, which we can really think of as like the minimum threshold required for a reaction. And then R and T have their usual meaning. Okay. So now if we flesh this equation out a little bit more and approach this from a couple different ways. One, let's suppose, so let me write that down first. So suppose EA equals 0. So if our activation energy equals 0, we have E raised to the 0 power, which is 1, and thus K equals A. So what that means is our frequency factor really is the frequency of collisions. So frequency of collisions. And in the limit where there is no activation energy for a reaction, the rate constant will proceed as quickly as the molecules are able to collide. So we often think of that as our diffusion limited case. So the only thing that's limiting the reaction is the speed at which the molecules are able to find each other and collide. So what that means is if K is a first order and has units of 1/seconds, then A must also be a first order collisional term. If K is in second order units, so which would be liter over mole per second, then A also has to have that same second order unit. Okay. And so now you might notice below me here, we've got our famous plot, natural log of some parameter versus 1/temperature. So if we adjust the equation up there accordingly by taking the natural log of both sides, I end up getting the following: natural log of K, and doing some algebra here, by taking the natural log of both sides, I end up with natural log of K equals negative EA divided by RT plus the natural log of A. So you can see here that's going to take on a Y equals mx plus B, where now my intercept is the natural log of that frequency factor, so I would be able to determine the frequency factor. And the slope is negative EA divided by R. So EA equals the negative slope multiplied by R, because EAs are always greater than or equal to 0. We don't have necessarily negative activation energies. Okay. So now if we proceed and take a look at this probably famous plot that you're used to seeing, potential energy versus reaction coordinate, or sometimes we could even put the quantity Z, right, the extent of reaction. We can see here a couple things that are going on. For one, in this example, if I look at the initial state of my reactants and the final state of my products, we could see overall this reaction would be exothermic, right? Because the final state is at a lower potential energy than the initial state. But also what we can see here is the energy required to get over the barrier. So the energy required for these to react is given by EA. Okay. So now that's an exothermic case. So what would an endothermic case look like? Well, we'd have reactants starting down here, and we'd have products starting up here. We'd have some type of barrier, right? So there's our initial, there's our final. So you can see our delta H is still given by the difference between the initial and the final state. So that would be endothermic, because now the potential energy of the final state is greater than that of the initial state. But now you can see our activation energy is quite large in this case. And it doesn't necessarily mean that all exothermic reactions have small activation energies, right? We just have to consider that we've got to get over that barrier. And so now something that you probably remember from Gen Chem, hopefully, or maybe even organic chemistry, when we introduce a catalyst into a mechanism, which we will be going through in great detail, the role of that catalyst is to lower the activation energy, which in effect will make the reaction go faster. So let's take a look at that Arrhenius expression again, e to the negative EA divided by RT. And now I've got a Mathematica simulator here that we can play with. So, and in this reaction right here, I put some stoichiometry. So this reaction for my model, so let me write that down, demonstration. The reaction was 2A goes to 2B plus C, I believe. Let's find it. Yes, 2A makes 2B plus C. Okay, so in this reaction now, you can see that nothing's happening because my frequency factor, that's the ARH, it's set to 0. My activation energy is set to 0, and my temperature is set to 0. So let's turn the temperature up on this reaction and see what happens. And we notice as I'm turning the temperature up, nothing is happening because I've turned the frequency factor off. So now let's turn the frequency factor on, and you can see I don't have to turn it on very much to get a reaction, right? So let's leave it at that kind of minimum value here. And now let's turn up the temperature. So this is still with an activation energy at 0. And if I make this reaction hotter, you can see it doesn't really do much because our frequency factor is quite large. So if I turn that up even more, now we can see that there's really little effect when there's 0 activation energy. And that's because the reaction is proceeding as quickly as it can given this particular frequency factor, right? But now if I turn on the activation energy, you can see I can effectively shut off the reaction by having a large activation energy barrier. And there's a couple of ways that I can overcome that barrier. So if I turn the temperature up, right, I can now see, if I get the reaction hot enough, it can begin to overcome that barrier and start to react. Or similarly, if I turn down the frequency of collisions, that slows down the reaction. Or if I increase the frequency of collisions, that speeds up the reaction. And then, of course, similarly, if I introduced a catalyst, by lowering the activation energy, you can see that that also has the effect of increasing the speed of the reaction. So there's a lot of ways that we can play with this and see how the temperature, the activation energy, and the frequency of collisions all affect the rate at which a reaction proceeds. And we will be exploring that in much, much more detail as we get into our section on mechanisms. I'll see you then.